we're going to be using calculus now to solve different kinematic problems. So from physics, you'll know that kinematics is the study of the motion of objects. So for our calculus problems, we're just going to be looking at when objects are moving in a straight line. So if we have a particle that is moving along a straight line relative to a reference point, we can label this as 0, otherwise known as the origin. So at any time t, we can measure the displacement from that origin, since the motion of our object is constantly changing. So we can see here we've got our object and it is moving, through time. And this is the total displacement or distance over that time here. So as we can see, we are increasing our distance as time goes on. So we know that for my average speed, it's the difference of my two points that I've travelled, as well as over the change of the time it's taken me to travel those two distances. Average velocity, on the other hand, is my change in position over my change in time. So velocity is more so concerned with displacement, whereas speed is looking at your distance travelled. And we can see this is just a straight line here. So we can use our gradient formula. So y2 take y1 over x2 take x1. But in this case here, instead of x's and y's, in replace of y's, we've got s at the point t2, as well as my function of s at the point t1, over my 2 points t2 and t1. So that just comes from my gradient formula. Of course, I've mentioned both the distance and displacement. So the difference between the two of these is that, for instance, I've got these this one particle, and the green represents its starting position, where the blue represents its finishing position. If I was talking about distance, this will be looking at just this orange line that's coming through here. So I want to calculate the total distance that has been travelled between each point. So for my particle starting at 3, the difference between 3 and 7 is 4. And then between 7 and -6 that it's now travelled coming back around here is 13. And then finally, the distance between -6 and -1 is 5. So adding all of this up together gives me 22 units travelled. So that's the total distance that my particle has travelled. Whereas on the other hand, for displacement, I want to look at the shortest change in position between my starting and ending points. So in this case here, I'm actually just looking at the direct distance here. So between -1 and 3, which is -4 units. So with displacement, we need to be thinking about its position in reference to where it's gone to where it's finishing. So this is -4 because I've started at green and I've gone backwards towards -1. So now that we know our difference between distance and displacement, we're going to continue looking at our velocity graph. So in this case here, this is our displacement, and again, we're going to be looking at the average velocity over time. So remembering back to when we did first principles, where we had our equation and we were just, again, still deriving this from our gradient formula. So instead of y2 in this case, I've got st plus h, so some distance h that we've gone forward. And my y1 is just s of t. So that's where we got this s of t plus h, take away s of t. And then we're saying that for my x coordinates, instead of x2 take x1, x2 is t plus h, and x1 is t. However, we know t take t would just give me 0, and I'd just be left with some distance h. This is just what our h represents, some random distance. I don't know what it is. And that's what we're finding. So this gives us our average velocity. So imagine if we just drew a straight line between these two and found the slope of that, that would give me my average velocity, or my average change of speed, I guess, over time. Of course, if we want the instantaneous velocity, we know that as we get closer and closer and closer to that point, then I need to be looking at as my h goes towards 0. So that's using this formula over here. One thing to notice though is that we can say that the velocity, of course, so as I get closer and closer to each other, of course, if I'm looking at one point precisely, that would be the tangent line, right? And we know that this tangent is the rate of change, which also relates to the derivative. So then we can say that our displacement function here, the derivative of that will actually give me my velocity function, as we can see over here. Similarly, if we were to draw another graph and it was to be of our velocity function, we would see that if we were trying to imagine the average velocity or change in velocity, we'd be looking at the average acceleration. So how much is that change of speed changing over time? So if we were to do that, my average acceleration is going to look a little bit like this. And of course, if we get closer and closer to the tangent of my velocity function, we'll actually find the instantaneous acceleration. So we can also say that acceleration is the derivative of the velocity function. So this means having a look at this all together. So if we started with our initial displacement function, if I took the derivative of that, I'd get my velocity function. And if I took the second derivative of my displacement function, so deriving this twice, I would actually get my acceleration function. So they're all related to each other, which is pretty cool. So of course, as we can see that each time the displacement function is differentiated with respect to time, a rate per unit is calculated. So for instance, we know that the units of velocity are meters per second. And we know that the units of acceleration are meters per second squared. So it's all related and interconnected to each other. So what we're going to be doing next is going through a few example questions of this and seeing what this looks like as we work through a few problems.
A particle is moving in a straight line so that its position x in meters at any time is given by the following function, which is x of t is equal to t cubed take 6t squared. As we are looking at time, we know that it has to be greater than or equal to 0. The first question is asking us to find the average velocity of the particle from t equal to 0 and t equal to 4 seconds. As it's asking us to find the average velocity, as shown here, we know that we can use the formula x of t2 take x of t1 all on the top of t2 take away t1. So I'm going to have that my t equal to 0, I'm going to make into my t1. And I'm going to have t equal to 4 seconds, that's going to be equal to my t2. So I'm going to plug these 2 points into my formula. So x of t2 is going to give me that 4 cubed, take away 6 times 4 squared, take, and x of t1 is going to be 0 cubed, take away 6 times 0 squared, all on the top of 4 take away 0. Simplifying this gives us 4 cubed is 64. Take away 4 squared, which is 16, times by 6 is 96, I believe. And we know that this part of my expression here is just going to become 0. So that's going to be all on top of 4. 64 take away 96 gives me minus 32 on top of 4. And that finally simplifies down to minus 8. And we know that the units for velocity is meters per second to the power of minus 1. So we can say that on average, our velocity of my formula between time 0 and 4 seconds is minus 8 meters per second. For part B, it wants me to find the velocity of the particle when t is equal to 2 seconds here. Because it's asked me to find the velocity at a certain point, that means I'm finding the instantaneous velocity. And remembering from our notes, my instantaneous velocity is actually the derivative of my displacement function. So I'm going to derive my x of t, which was t cubed, take away 6t squared. So deriving this to give me my velocity function gives me 3t squared, take away 12t. Now specifically, I want to find my velocity at t equal to 2 seconds. So this is going to be 3 times by 2 squared, take away 12 times by 2. 2 squared is 4, times 3 is 12. So 12 take away 24. So 12 take 24 gives me minus 12 meters per second to the power of minus 1. So I can say that my instantaneous velocity at the point t equals 2 is minus 12 meters per second to the power of minus 1. My next question is asking me to determine the time intervals for when my particle's velocity is positive as well as when my particle is negative. Now essentially this is asking me to find the different signs of my function. And I know that I can use a sign diagram to do this. To find my points though for my sign diagram, I need to have for when my velocity function is equal to 0. So grabbing up my velocity function, this was 3t squared, take away 12t, and I want this to be equal to 0. So 3t squared, take 12t equal to 0. And I'm going to take out a factor of 3t from here. So I'll have 3t, and in brackets I will have t take away 4 equal to 0. So therefore, I'm going to have some critical points when my t is equal to 0 and when my t is equal to positive 4. So putting these onto a sign diagram, at the very beginning here, that's my t equal to 0. Now, as we know previously, we cannot have time to be less than 0. So I'm going to just draw some lines here that represents that my t cannot be any smaller than this. And that also comes from the domain that we're given up here. And I'm going to have another point, which is t equal to 4. So I'm going to plug in for this point for my first one when my velocity function is equal to 1. So putting it into my velocity function, I've got 3 times by 1 squared take away 12 times 1. So that is just 3 take away 12, which is going to give me a negative here between 0 and 4. For my function greater than 4, I'm going to plug in the number 5. So my velocity function at the point 5 is going to be 3 multiplied by 5 squared, take away 12 times by 5. 5 squared is 25, times by 3 is 75, take away 12 times 5, which is 60. So this is going to give me a positive here. This makes sense as my velocity function up here is a quadratic, so I should be seeing a change in signs. So because it's going to from a negative to a positive here, I know that this must be, in fact, looking a little bit like this. So must be a local minimum. However, my question doesn't quite ask me this. It says determine the time intervals for when the particle's velocity is positive. So I can say for my first one that therefore my particle's velocity is positive when my x is, not my x in this case, so when my time t is greater than 4. And I can say that my particle's velocity is negative when my t is in between 0 and 4. So moving on to my last one, so find the acceleration function and hence determine my acceleration function at the point when t is equal to 3. So remembering from our notes that my acceleration function was actually equal to the derivative of my velocity function. My velocity function t is equal to 3t squared, take away 12t, which means the derivative of this is going to be 6t take away 12. And of course, I know that this is equal to my acceleration function. So 6t take 12. When it is at the point time equal to 3, I'm going to have 6 times by 3 take 12. 6 times 3 is 18, take away 12, which means that 18 take 12 is 6 meters per second to the power of minus 2. So at the point when my time is equal to 3, I can say that my acceleration is actually positive. So now we've finished these examples. I hope that you have a go at some of the other questions that have been set for you all to complete.